Cambrian-Ordovician, Episyenites, and carbonatites in southern and central New Mexico, United States of America. And I do want to, acknowledge some of the students that worked on this project in the past. It was Adam Smith and Annalise Riggins. Of course, my director worked on this project before she became director, Amelia Dunbar, and Matt Heisler did supervised a lot of the age dating that I'm going to talk about. And then my friend from the University of Helsinki, Tapani Ramo, also did some neodymium isotopes. As I said, there's a number of students that worked on this in the past, including during COVID. Jonas Claire Ramusen did a senior thesis, and he did some uranium lead dating, which I'm going to report. And he's with he was with the University of California at Santa Barbara. A few other students have worked on it. We've got Eric Ruggles that's working on the Lemitar carbonatites today. And various sources, we put together a lot of funding. We've had some Czechoslovakian geologists come out and work on some of this, and their Science Foundation funded some of this work. Certainly SEG, and as I said, it was one of the USGS external research programs before the Earth mapping project came in. So let's get started. As I try to tell my students, one of the things we all get hung up on is definitions. And so it's boring, but at the same time, at least you know what I'm talking about. And so first, critical minerals, because this is, the fundamental, what's behind all of this. And critical minerals.
You want to sit in on this, Pat?
Critical minerals are minerals that are needed for military, industrial, or commercial purposes that are essential to energy, to our national defense, to our economy in general, but they are subject to potential supply disruptions. And these minerals form an essential function for which there are few or very few or no satisfactory substitutes that are around. And the absence of these minerals would cause economic, national security, or social consequences, a world that we don't really want to live in. There's about 33 to 50% of the commodities that really fall into the realm of critical minerals. What I've done here is shown that in 2020, the last administration came out, asked that the Department of Interior, namely the U.S. Geological Survey, to come out with a list of critical minerals. And what I've done in these two is shown the list in 2020 and then the list in 2022. And I've color-coded them mainly by color code on what was produced in New Mexico. And so in the past, in 2020, we had potassium listed. Well, potassium was dropped in 2022. Potassium is mostly used in fertilizer. The other elements in blue were once produced from New Mexico, and then the elements in green we find in New Mexico, and the yellow, we don't really know that we have them in economic quantities in the state. So this gives you a rundown of what is behind all of this research that we're talking about these days. I do want to emphasize that these critical minerals will change with time, and they also change with country. In the ancient past, in ancient times, salt was once a critical mineral. But now, of course, no one thinks about salt as being a critical mineral. Copper is definitely considered a critical mineral by Japan. And there's a number of people that think copper could become on a critical mineral list here in the United States in the very near future. We shall see. The next term I want to define is episyenite. So this is a term that's been around since 1920. It describes metasomatic rocks that have a syenitic composition, but the magmatic protoglyph is really not certain. And as more and more research is being done on these rocks, they're not igneous origin. They are.
Yep, I'm on.
They are a metasomatic. They're metasomatic formation, and I hope to convince you of that before the end of the night. The ones in New Mexico I'm going to talk about are quartz depleted, K-feldspar-rich, altered rocks that were desilicified and metasomatized by we're thinking of alkali-rich fluids. They're similar to the altered rocks, And they are similar to a process called fenitization, that is the alkali metasomatism associated with carbonatites or alkaline igneous activity. But we're really reluctant to use the term phenite for these rocks because we don't see a clear association with carbonatites or alkaline igneous rocks. And we'll take a look at these in more detail here in a few minutes. But here you can see the upper left, upper right is a dike-like episyenite in the Caballo Mountains, and then you can see some additional episyenites in the lower one. Now, carbonatites are an unusual type of rock. It's an igneous rock. They are carbonate-rich rocks that contain greater than 50% magmatic carbonate minerals, mainly calcite, dolomite, siderite, anchorite, apatite, barite, and other minerals as well. And they are less than 20% silicate minerals, so they are very silica poor. And we know that they are a magmatic, is that we really do have a volcano that is erupting carbonatite lava in the East African Rift. And so it's interesting to make those comparisons. What's important about carbonatites is that that's where most of the rare earth element production is now occurring. And that is from Bayan Obo in China, and then here in the United States, Mountain Pass in California. And this is a large source. Both of these carbonatites are large sources of rare earth elements. So as you well know, if you've got a type of rock that has rare, known to have production, you're starting to look for them throughout the country. So let's get on and taking a look at some of these carbonatites. Some of these carbonatites and episyenites. These are episyenites in this picture that are in the Caballo Mountains. And what I'm going to really try to show you tonight is what the origin of these rocks are. Are they magmatic or metasomatic or both? Go into some of the mineralogy. We'll also talk about the carbonatites, and then we'll end with kind of the mineral resource potential, and then how I think these guys are being formed. And to do this, it's taken a team, as you've seen at the very beginning slide. It's a lot of field mapping and sampling, and I just cannot emphasize the field work that goes into this. But then we have petrography, we have whole rock chemistry, X-ray diffraction, electron microprobe work, and then radioisometric dating and neodymium isotopes as well. So we think that these, from the age dating and from some field relationships I'll show you, that these are all part of a Cambrian-Ordovician magmatic event in New Mexico that resulted in carbonatites, syenites, alkali granites, and these episyenites. And we find them scattered throughout the state and also into southern Colorado, where we have fairly large carbonatite complexes exposed. Iron Hill is one that is currently being looked at for the niobium resources. And what we think is that this was a failed allocogen during Cambrian-Ordovician times, essentially the breakup of the continent at that time. So let's take a look at some field relationships. Here you can see the episyenite in brick red color that is in very sharp contrast to the metamorphic rocks that are found in the Caballo Mountains. And we've done a lot of mapping on these. These are in the Caballo Mountains, which is in central New Mexico. And you can see that they do sometimes seem to form trends, linear trends. A lot of times they form pods, and we have sampled a number of these. Here you can see at Apache Gap, one of them that's forming kind of a pod-like. And these are very distinctive, and I'm sure they're found in a number of other places throughout the country. They're just not recognized for the rare earth potential. And here you can see such a sharp contact between the brick red episyenite and the Caballo granite and the to the right of on this slide here. Here we can see the episyenite, and this one is occurring actually at the junction, the intersection of the long bottom canyon granodiorite and Caballo granite. And we really think that some of these very much are related to contacts between different granitic units. We also see some of these episyenites in the field where they very abruptly, they're this brick red, pegmatites have a lot of quartz in them. This pegmatite is episyenite. The quartz has been removed, and the feldspars are potassic feldspar, and it grades very quickly into an unaltered pegmatite. And these are the kinds of field relationships we see in most of these areas in the state. One of the neat things is that in the Caballo Mountains, we do see that there is an unconformity on top of where these episyenites occur. So the episyenites are found in Precambrian rocks, and we have this unconformity between the Proterozoic and the Cambrian-Ordovician bliss formation. And the lower part of the bliss is a basal transgressive conglomerate. And what is really neat in some of these areas in the field, we actually are finding some fragments of these episyenites in this basal conglomerate. And even more important, we actually have looked at probe work, and we have found some of the rare earth minerals are indeed in the basal conglomerate as rock fragments. And when we do the mineral chemistry, in this case, the xenotime has exactly the same chemistry of xenotime that we find in the rock fragments in the bliss as the xenotime that we find in the Proterozoic rocks. So we have clear evidence that field relationships that show that these are Cambrian-Ordovician or older. When we also look at the probe work, we find that the secondary K-spar, which we see here, is very clear and a newly formed K-spar. The older original feldspar has a lot of inclusions with it, and you can see quartz inclusions in this. And this is really important because it shows that these feldspars must be carefully selected. If you just grab a feldspar, you could be actively dating both the newly formed K-spar as well as the old original K-spar. So argon has proven to be quite challenging in some cases. When we take a look at some other field relationships over in the Burro Mountains, we see that these episyenites often form the caps of some of these ridges in the Burro Mountains, and this is just north of the Tyrone copper porphyry deposit. But this is, in Proterozoic rocks. And when we look at it in detail, the host is a Rapakivi granite in this Ramsey Saddle area. And you can see the Rapakivi texture in this granite, and you can see that the texture is still preserved in the episyenite. And this is, some very definite field relationships that show a metasomatic origin. The episyenites generally, in this case, this one is almost 14% K2O, whereas in the original granite, it's more of a 6% K2O. So we definitely have had silica removed and potassium added. In the Zuni Mountains, we see some interesting field relationships. We often see these trains in the episyenite, these vuggy zones. And this is what we're interpreting to be fluid movement that is perhaps forming these episyenites, or it is fluid degassing at the last after the metasomatism has occurred. And once again, in the Zuni Mountains, we're seeing them often forming these caps on these ridges. What's interesting in the Zuni Mountains is that we have both metarhyolite and Zuni granite, and we do have very good uranium lead dates as well as KR dates. That the metarhyolite is 1.6 billion years and the Zuni granite is 1.4 billion years. And both of these lithologies have been altered to episyenite. Also in the Zuni Mountains, you can see some of these textures and some of the very coarse grain. And then, as I said, this vuggy breccia that we see. And we see this vuggy breccia also in the Burro and the Caballo Mountains. We are currently working in the Zuni Mountains doing some stream sediment survey under the Earth MRI program. And so we will see if we can find any additional areas in the Zuni Mountains. Now, the carbonatites we find in several areas in the state, the most predominant which is in the Limitar Mountains, just north here of Socorro. And once again, the carbonatite dikes have intruded a very complex Proterozoic, granitic, and metamorphic terrain. And these dikes are up to 1 meter to 1.5 meters wide, and they do have elevated concentrations of rare earth elements, uranium, thorium, and niobium. And they have been dated as Cambrian-Ordovician. So they are part of the same event. Let's talk a little bit about the chemistry and the mineralogy of these, both episyenites and carbonatites. Here you can see one of the episyenites again in the Caballo Mountains. So in the Caballo Mountains, we find that these episyenites have quite complex mineralogy. All of them have K-feldspar, and all of them do show a lot of brecciation. A number of them show chlorite and some calcite. But then in the Caballo Mountains, we do see quite an abundance of synchrosite, asynchrosite, xenotime, thorite, uranophane, and bastnasite. And these are all minerals that can contain rare earth elements. And indeed, we do see elevated rare earth elements in the Caballo Mountains. In the other areas, the rare earth elements are not as concentrated or as high as they are in the Caballos. And we have put together a paragenesis of these minerals. We do see that some of these minerals do appear to be, like xenotime, is quite early in the metasomatic event. Here you can see some of the uranophane and some of the fluorite that we see in some of the Caballo episyenites. When we look at them in probe, it really shows up. You can see here that, let's see, we've got, this is one of the elements that we see, and you can see that the rare earth rims are surrounding iron oxides. And once again, quite supportive. Here's rare earth element rims surrounding this iron oxide. And this is quite supportive of a metasomatic origin. Let's see. There we go. And here's some of the zircons that we see. And once again, these zircons contain some of the heavy rare earth elements. These bright specks appear to be xenotime. And we also see other elements associated with them as well. And these zircons are zoned. And it would be good to do some laser ablation work on this and actually see if we're looking at zircons with an older core, and then the growth is representative of part of this metasomatic event. Here's another electron microprobe image, and this is one of the most compelling of the evidences of these rare earth elements in these episyenite. Here we on the slide, on the graph up to the upper left, we see the actual mineral chemistry of synchrosite and thorite. And then the next two photos on the upper right and middle are false element colors, showing that the green here is synchrosite, the blue is thorite, which is surrounded by xenotime, and then the red is just iron oxides, and then we have some of the zircons that are shown here in the bright images. So this is very complex mineralogy, even though it's a metasomatic event. When we look at the geochemistry, these episyenites are shown here in red. They are quite enriched in potassium, although we do see a few sodium episyenites, and certainly in the world, there are, the literature does describe some of the sodium-rich episyenites. So it's not just a potassic metasomatic event. But these high K2Os are just not representative of igneous rocks, especially with the low sodium. And this is found, the upper one here is in the Zuni Mountains, and the one to the right is some of the chemistries in the Burro Mountains. And we plot some of them, and you can see indeed that this is in the Caballos. This is the Caballo granite, and you can see the K-feldspar variations of these metasomatic rocks. Another rather interesting thing is that these things are elevated in light rare earth elements, But then every now and then we see some heavy rare earth element enriched episyenites. And these heavy rare earth enriched, that is close to ore grade for some of the deposits. Now, we haven't found enough of these heavy enriched episyenites to be considered a deposit, but it certainly is interesting. And it, who knows what's at depth, but it also may be showing that this metasomatic event could be one way of concentrating the heavy rare earth elements. And here's just two more of the episyenites, the chondrite normalized patterns. You can see how enriched this particular one is in light rare earths and how enriched it is in heavy rare earths. There's as much as 11%, 11,000 part per million of total rare earth elements in the Lemitar carbonatites. And the mineralogy in the Lemitar carbonatites so far we know is bastosite. But certainly Eric is going to be working on some of the more advanced mineralogy and doing some probe work on this. But you can see that some of these patterns in the Lemitar carbonatites are up to 10,000 parts per million, or rather 10,000 ratio, 100,000 ratio. And these are, Mountain Pass has, 5 to 15% total rare earth elements as grade, and the Lemitar carbonatites are 1%. Once again, they haven't been drilled, so we don't know exactly what all is, how extensive they are at depth. There's also over 1,000 parts per million niobium, and these are very barium rich as well. They're certainly not economic at the present time, but they do have quite interesting chemistries and mineralogies. And when we look at the other carbonatites from throughout New Mexico that are of the same age, they do appear to be, for the most part, solvite and ferrocarbonatites. And that's just based on the international classification. We also have identified a thin carbonatite about a foot in width, and it's only about a couple hundred yards long in the Caballo Mountains near some of these episyenites. I was reluctant to call it a carbonatite until Emily Perry actually did do some work on the calcites, and she did find that they are indeed, not only are the calcites enriched in rare earth elements, there are 4 stages of the calcite, and they are magmatic calcites. So we have another locality of carbonatites in the state. This is what the Lemitar carbonatites look like. They are can be quite enriched in phlogopite. Here you can see some of the apatite and magmatic. These are magnetite. These are magmatic minerals, as well as the amphibole and the additional phlogopite. So we have put out an article, a couple of papers on this, and we are very confident that the Lemitar carbonatites are indeed magmatic carbonatites. So let's take a look at the age relationships, and I do have to, the students, Annalisa and Adam Smith, are the ones that did a lot of the argon-argon dating under Matt Heisler, and Jonas did some of the uranium-lead dating. And these are what's really compelling that shows that there is this Cambrian-Ordovician alkali event in New Mexico. Here we can see some of the messy argon-argon dates. And messy, I mean, they're not the most cleanest patterns you want, but like I said, that's the problem with trying to date feldspars. And we get a wide range of dates as well. We get as young as 34 million years, and in the Cambrian-Ordovician ages around 500 as well. And so these are very messy. And what I think was dated was a mixture of altered and new metasomatic of the original feldspar, and also it had some of the alteration associated with it. And then the other problem that we do have with argon-argon is the closing temperature of K-feldspar. These are, like I was saying, these are messy argon-argon patterns, and they certainly are showing different ages, and they are feldspars. And I think they're dating both old and new metasomatic feldspars. And I think that's also what's happening here in the Zuni Mountains, where Strickland presented this age of the syenite. She called it a syenite, but it is indeed an episyenite as 1.1. And I think that we have predominantly an original feldspar that she dated. In the Florida Mountains, we were lucky in that it is a Cambrian syenite, and Jonas was able to confirm a Cambrian-Ordovician age of 511 with some of the argon and the zircon dates done previously of about the same age. So we do have a magmatic syenite in this area as well. We also see some of these magmatic syenites, like I said, up in Colorado. At Lobo Hill, we do have somewhat of an age of 500 million years on one of the episyenites, but we also do see 300. So you're just kind of guessing. And the muscovite is representative of a 1.4 granite. But once again, Jonas was able to get a sample, and he actually found a zircon that does represent the Cambrian-Ordovician in age, and he was able to get a 520 million year age on one of the episyenites on zircon, and that matches very nicely with a 518 million year age of an argon of biotite in one of these episyenite bodies in the Lobo Hill area. The Burro Mountains, we have a nice Cambrian-Ordovician age from one of the episyenites, and this is actually the evening star. And this area is an area that we are now mapping as part of the Blackhawk district. So we do hope to have some more information on these episyenites as well. And the Lematar, we have both a very good argon date on phlogopite of 516 million years in age, and we have a uranium lead date 514 on a zircon. So we definitely have primary magmatic rocks of Cambrian-Ordovician in age. Now, Tapani Ramo did some of the nididinium isotopic data, and I can't answer too much questions about it. This is his plot. But essentially what the take-home message is that the Lematar carbonatite does appear to be from a relatively strongly depleted mantle and a quite different source than the episyenites. And here you can see the episyenites. These are all from the Caballo area down in just south of the of Socorro here. And these are much less radiogenetic, and they record a dramatically different but enriched source, probably a cratonic subcontinental lithosphere. So according to the nididinium isotopes, we're looking at different sources, even though these rocks are of the same age. Just very quickly, just to emphasize, these are not economic. They have not been mined. The carbonatites, we do have up to 1% total rare earth elements, due mostly to bastnasite. We do know that the chemistry is probably quite complex, and we've got a student working on that. We do have over 1,000 parts per million nididinium. Do not know where that nididinium's at yet. That should be ND, sorry, not MB. It is nididinium. And they are enriched in barite, which both Mountain Pass and Bayan Obo are quite enriched in barite as well. So these concentrations are elevated, but they're not economic at this time. The episyenites, once again, we're not saying these are economic deposits, but they are certainly a different type of deposit that does carry elevated rare earth elements. It is a quite complex mineralogy. They were originally located because of the some of the uranium contents, and we do see some quite elevated uranium contents in some of these. So for the origin of the model that we're kind of working with right now is that, and I want to go to the, see if I can go to the view, because it shows the colors very nicely. Can you see that slide fine?
Mm-hmm. Yes.
Okay, so we think that what happens is that we've got these fluids perhaps coming from a carbonatite or an alkaline igneous melt at depth, shown here in red, and that these fluids are the hydrothermal fluids that are coming off. They are migrating along fractures, um, maybe even the contacts like we see in the Caballo Mountains of different Proterozoic granitic plutons. They metasomatize the rocks at closer to the surface. Of course, we have erosion down now to where we're actually seeing the episyenites. We do not see the original fluids that are causing the metasomatism. And they do appear to be of Cambrian-Ordovician of age. This is a map showing where a lot of these are found. A couple of them like Iron Hill, McLemore Mountain. McLemore Mountains, we definitely see phenetization and what we would call episyenites. Here in the, we just see carbonatites at Monte Largo, Lobo Hills, now Caballos, and in the Lematar and Chupadera Mountains. We've yet to find them in these other areas, but we're going to keep looking. So in conclusions, what I like to do is that episyenites or carbonatites in New Mexico and Colorado are Cambrian-Ordovician, and they are associated with Proterozoic granitic and metamorphic rocks. They are brick red in color, they are metasomatic in origin, and they are possibly related to alkaline or carbonatite intrusions at depth. Otherwise, we've got to figure out how we're getting quite alkaline fluids that are altering these rocks to 14%, 15% K2O. There certainly could be multiple fluids of different ages, or even an evolution of metasomatic fluids over time. And I certainly would not argue that some of these may not be of Cambrian-Ordovician in age when we don't have clear dates. They certainly, when you start looking at potassic alteration, that is a common type of alteration. So we do need to be careful. But sampling of these rocks is critical, and really making sure you get the right samples so that you can date the proper minerals. The rare earth mineralogy is quite complex. I didn't go into it too much, but it is the rare earth minerals are associated with amphiboles. We did see some of them associated with magnetite and the zircon. And fluorite is also a component of some of these episyenites. Surface samples have low to moderate total rare earth elements, thorium and uranium. Their niobium appears to be quite low in the episyenites, but some of these samples may have relatively high, heavy rare earth elements. And those heavy rare earths could be indicative that this metasomatism could be a mechanism to concentrate heavy rare earth elements. We'll just have to do some modeling and some isotopic work. Drilling and subsurface sampling are certainly going to be required to fully evaluate the mineral resource potential of these areas. The carbonatites in the Lematar Mountains, they are dikes. So there's not the volume at the surface, whether there is a pluton at depth, that is kind of the hope, but there is up to 1% total rare earth elements found in some of these carbonatites. The episyenites and the carbonatites in New Mexico are not economic. Drilling is required, but certainly the Iron Hill, which is also Cambrian-Ordovician in age in Colorado, that is an economic resource of niobium, and it's 1.2 kilotons of 0.05% niobium oxide is what the company is currently reporting as a resource. So I guess with that, I will take any questions. I haven't paid attention to the chat, but let's see if I can see it now. Yeah, just about the slide's not showing. So, okay. I will take any question.
Ginger, that was marvelous, and I think I'm looking at the chat too. I don't see any questions there unless I'm missing something. So perhaps this would be the time for people to unmute themselves and throw out a question. So please.
I have a question.
Dave Briggs has one.
Yeah. number of years ago, I did some work in the Caballo Mountains looking at barite veins that are in lower Cambrian, I think, or lower Paleozoic for sure. Is the barium there related to these things in any way?
So the Caballos are kind of an unusual area in New Mexico in that there are so many different types of deposits that are overprinting one another. So we have what we think are Precambrian gold silver veins. We have these episyenites that are Cambrian-Ordovician. We have jasperoids that are Silurian in age, maybe maybe even going up a little
Ginger,
bit
can
more.
you hear me? This is Will Wilkinson.
Yeah, I can hear you, Will. So I'm not sure exactly where the barite fits in. We do know we have very recent barite fluorite galena veins as well in there that I attribute to the Rio Grande Rift. There is barite associated with the episyenites.
Yeah, I am the area that I was thinking of. It's pretty close. It's just east of Hatch and access by road from Hatch.
Okay, so there is a barite deposit down there that is let's see, it is there's actually a company looking at it for barite. It doesn't have
Ginger,
as
can
much
you hear me?
fluoride
This is
in it.
Will Wilkinson.
Yeah. That barite deposit I think you're referring to closer to Hatch is probably Rio Grande Rift barite fluorite galena deposits.
Okay.
And not related to the episyenites.
Okay.
That's my feeling on them. And there is a company that's been looking at them apparently for looking at drilling muds, for using drilling muds, but that was before COVID, and I haven't seen activity.
I looked for drilling muds early, late 70s, early 80s.
Yeah, but there's just a lot going on definitely in the Caballos. There's even some vanadium molybdenum in there as well as veins. And someday maybe it'll come to the top of the list under Earth MRI and we can do some work in the Caballos.
Will, did you have a question? Because we could hear you.
Yeah, I was looking at this and thinking about the red rock alteration, which is fairly typical of iron oxide copper gold deposits, which also have some exotic elements with them. What is there any relationship between these two in your point of view?
So like I said, Americans really aren't recognizing episyenites per se as a type of alteration or mineral deposit, but the Europeans have, and they have for quite a number of years. And yes, this type of metasomatism is related to tin deposits and to these alkaline gold type deposits. So yeah, and there's a whole body of literature. A lot of it's in foreign languages that I haven't had translated, but it is a metasomatic alteration, and certainly alkaline fluids are not, strictly related to just carbonatites or to rare earth deposits. So I would say yes, it needs more study.
Yeah, because if you look at Olympic Dam, it's high in uranium and some other things. Yeah, so.
Yep. And I'm even seeing some of this metasomatism that might be related to some of the Blackhawk 5 arsenite vein system, but I'll leave that one and see where we go with our mapping on that. This overprinting of different types of deposits definitely causes some interesting challenges.
Thank
Hi.
you.
Hi, this is Marta. I have a question. How related are the syenites to A-type granites, which can be found in a similar trend that you presented at the beginning?
Yeah, so most of these Precambrian terrains that we see the episyenites in, the episyenites are altering A-type granites. So that's where the connection is. They do seem to be a host. We do see some of these episyenites in some of the metamorphic rocks, and like I said, in the pegmatites. But for the most part, I think everyone is calling a lot of these granites definitely A-type 1.4 billion year old granites that are quite characteristic of Proterozoic terrains in the Southwest.
But my question could be more, for example, if we have granodiorites and we have the equivalent in volcanic rocks to andesites, why we are calling like alteration the phonolites and all these rocks instead of just the extrusive expression of the A-type granites?
So first off, the A-type granites are 1.4 billion years in age, whereas we're seeing these metasomatic episyenites are around 500 million years. So we have a difference in age. We have differences in chemistry and mineralogy. And I certainly will not argue that this metasomatism could be characteristic of other types of mineral deposits. They are not igneous, original igneous rocks. They are altered igneous rocks. So did that answer your question?
Well, not quite, because they have a specific, as you say, chemical features that can give them that specific characteristics. But I mean, for why I understand the A-type granite have also, as any other type of igneous, I don't know, bodies or magmatism, has a volcanic expression of them. So it's not, and also there are also A-type granite that has been dated not like too old. They're actually kind of related with the extension in the region.
Yeah, no, I mean, we've studied a lot of these A-type granites. Like I said, we have the difference in age between the A-type granites and the episyenites. And we don't know what the source of the metasomatic fluids are. They certainly could be a differentiation of alkaline fluids coming off of A-type granite of Cambrian-Ordovician in age. But right now, the rocks that we see that are Cambrian-Ordovician in age are syenites to alkali granites. And we just don't have enough of them to really be able to sort it out. So that's certainly something you would want to be looking in other areas of A-type granites to see if you see these metasomatic rocks.
No, just to put an example, I read a paper of you from the Cornudas Mountain that is in the limit between New Mexico and Texas.
Right.
And those rocks are not too old.
That's right. They are about 30 million years in age. I just put out an open file report summarizing some of the Earth MRI work we've done there. There is none of this K alteration, potassium metasomatism associated with those rocks at all in that district. And
those, Ginger, let me ask you. Oh.
Yeah, those aren't even A-type granites. That's a definitely alkaline system, nepheline syenites.
Ginger, are you familiar with any epicyenite deposits over here in Arizona?
Well, there's that one along the interstate that I drive by and I want to stop every now and then and look for, I think in the Dragon Mountains maybe, or Dragoon Mountains.
Right.
When I drive to Tucson, I think they need to be sampled and looked at. That's the only one that I've really found any evidence where I've seen it, but my sandbox is in New Mexico, so I haven't been over there to Arizona as much as I'd like.
Okay, thank you. Are there other questions for Ginger before we let her go?
Ginger, yeah, this is Floyd. There was a chat question, and I had the same question about fluorite, and how that relates to some of these deposits. And is that on the edges or is it in the core of the systems at all?
mostly I see now in the carbonatites, the fluorite appears to be magmatic. And we'll see if
Okay.
if the student can make any headway on showing whether it's magmatic or indeed a hydrothermal mineral. In the episyenites, I see two forms. I see some of the vein type fluorite, which could be of any ages, including the recent Rio Grande Rift type fluorite deposits. There's no telling. There is a method we can date fluorite, and it would be nice to get some of those dated. But we also see disseminated fluorite in the episyenites as well. And I will also, in most of these areas where we see the episyenites, we definitely have younger fluorite.
What time is it now?
deposits.
7:24? It's only been an hour.
So that answer your question, Floyd?
Yeah, that's good. I was wondering if they were there. I guess it was more important to talk about the other stuff. It sounds like they're very late and just maybe a much later overprint of some sort.
Right. Yeah. I mean, overprinting is a big thing along the Rio Grande Rift. It is just incredible the amount of different mineralizing events and just hydrothermal events. And so somebody that jumps into New Mexico and starts studying something, they just do not appreciate that overprinting.
Yeah.
And how you sort all of that out. And that's, some of our problems in both the in the Burro Mountains, where we're looking at mapping the 5 arsenite vein systems, as well even up in the Zuni Mountains, where we just have a lot of different overprinting. And sorting the different types of mineral deposits takes a lot of time and chemistry, and ultimately it's going to take isotopic methods as well to sort it out, which we're not even going to touch right now.
Next, if I could just ask what next in the next couple of weeks, I guess Mark's going to bring some of the Earth MRI geophysics, and maybe you can resolve whether some of these carbonatites have plutons underneath them at some point.
Yes, we're looking.
He's got a lot of processing that he's doing that might show that.
Yep, that would be really great.
I have a last question, and I don't want to bother, but this is something that is in back of my mind all the time. Do you think that in the future this can be like a source of critical minerals for United States?
So at Lobo Hill, one episyenite, it's actually a crushed rock, an aggregate quarry, and the guy has that beautiful red episyenite is a aggregate that is quite useful and desired by a lot of companies for decorative stone. And so he has drilled it, and he's been slowly mining it, and we're finding that particular pipe is at least 60 feet deep and 30 feet in diameter. So these pipes that we're seeing at the surface, they could be representative of larger volume deposits at depth. It's just going to require drilling. And so at this point, it's just a matter of grade and tonnage. And at the surface, we have no idea whether that grade or tonnage is there. It has to go to drilling.
Ginger, it's Will Wilkinson again. So looking at one of your slides, petrography, and looking at the differences in the K-feldspars, is that where you need to start before you start age dating these things and separating out those?
Yes, you really have got to take a good look at that feldspar and make sure that you have a good, clean feldspar. And even then, you're still looking at, some of the closing temperatures and some of the difficulties, challenges of dating K-feldspars. And we're even seeing the same kind of problem with zircons. If you saw how zoned that zircon is, and I would really like to see very detailed dates of the different zonations in those zircons. And I would hypothesize that I would think that we would see a core that is 1.4 or even older, and that we've had zircon growths around there during Cambrian times. That would be really cool if we could show that.
Hey, Ginger, Vince Matthews has a question for you.
Yeah, I see Vince's hands up. What's up, Vince?
Hi, Ginger. That was a great presentation. This is an off-the-wall one. I really am not clear on how much range in question there really is on the dating of these things. One of the things that strikes me very strongly is that these seem to be associated with the Rio Grande Rift. We know that carbonatites are very prevalent in the East African Rift, and I just wonder if is there enough data to really rule out that these things aren't associated with the Rio Grande Rift?
I really think that there are. I mean, Chuck Chapin and I have gone over this time and time again too, because certainly you do have carbonatites related with the Rio Grande Rift, and that was why we were able to get a date very early on the phlogopite and the carbonatites. And I think that, you know, between uranium lead and the KR, I feel very confident that we definitely have Cambrian-Ordovician, Episyenites, carbonatites, and syenites. And we have the field relationships in both the Florida and the Caballo Mountains. We've got Cambrian-Ordovician sitting right on top of the Cambrian syenite in the Florida Mountains, which is a magmatic igneous rock. And they're in the Caballos. That field relationships are very compelling, that those are older than the Cambrian-Ordovician bliss. I mean, we're seeing the episyenites in the Proterozoic rocks, and then we see the same mineralogy and the same mineral chemistry of episyenite fragments in that bliss formation. Now, whether the other areas, I think you're very much true that we can make an argument that in these other areas where we don't have those really good field relationships or the really concrete dates, like in the carbonatites, certainly some of those episyenites could turn out to be other ages.
Okay,
But
thanks
we're
very
not,
much.
yeah, we're not seeing that metasomatism associated with Rio Grande Rift magmatism. So we don't see that with what we know as, you know, alkaline rocks associated with the Rio Grande Rift.
Okay,
So,
thanks.
of course, that's negative evidence, but it is supportive. So, and I think that it's more than a coincidence. I think that during Cambrian-Ordovician time, we had an allocogen, a failed rift. It started to rift, it started to break apart, and it didn't for some reason. And the Rio Grande Rift has taken advantage of those precursor fractures and zones of weaknesses. So I think that's where the connection is that we're looking at reactivation.
Great.
Are there any final questions before we let Ginger go for the evening? Well, Ginger, thank you so much. That was a marvelous presentation, and I'll keep you informed as to when it's ready to go up, and you'll have an opportunity to look at it first.
Yep, and I hope to talk more about some of this to all of you guys when we meet in person, which will be sooner for some of you than others, but certainly we'll all get together at some point. So thank you very
good.
much. Thank you for your questions, and let's think more about these guys.
Thanks, Ginger.
Thanks.
Ginger, thank you, and we'll see you at the New Mexico Minerals Symposium.
Thank you.
That we will. Okay, good night, everybody.
Good night.
Good night.